All right, welcome everyone to class 34, the final class of this semester here. Yes, we've almost made it. But the last thing we're going to talk about is one of my favorite topics in this class here is improper intervals. Right, so it seems to connect a lot of ideas that we've learned this term here. All right, so this name here, improper integrals, right? It's so improper. First, what we're going to do is we're going to talk about those ideas there. So the type of integrals we have been talking about so far have been finite valued. So they've been nice integrals. All right, and we have been working over finite value integrals over finite intervals. All right, so meaning whenever we have integrated something, it's been from 1 to 3, 4 to 5. In this section here, what we're going to do is we're going to extend this idea of a definite integral from finite valued functions on finite intervals to incorporate infinite valued functions on infinite intervals. All right, so really what we have, the integrals we have been talking about so far have never had any infinite discontinuity. So whenever we want to integrate something, the definite integrals that we have talked about never have had infinite discontinuity, because we don't know how to deal with those. And we have never talked about integrating a function over an infinite interval. All right, so let's look at a few examples here. So first is we are going to look at this integral here, which goes from 1 to infinity. All right, so this function here is continuous on this interval here, right? So the only way this function is discontinuous is if the denominator is 0. And is that 0 in this interval from 1 to infinity? No. However, we are integrating it over an infinite interval. Right? So this is what we call an improper integral of type 1. Similarly, if I look at this here, 1 over 1 plus x squared, this function is always continuous because the only way we could make the function discontinuous is if the denominator is 0. And in this case here, the denominator is never 0 because it's always positive. However, we are integrating from negative infinity to positive infinity, so our interval is infinite. Right? So again, these are examples of what we're going to make this precise here of type 1 improper integrals. Now next up, let's look at this interval here. We're integrating from 0 to 1. Right? So this is a finite interval here. However, if we look at our function here, 1 over square root of x, what happens at x equals 0? This function has an infinite discontinuity at x equals 0 because it has a vertical asymptote, right? Because limit as x approaches 0 from the right-hand side of 1 over radical x is positive infinity, as shown by this picture here. So in particular, this is going to have an infinite discontinuity at 0 here. So this is an improper integral of type 2. Again, like I said, we're going to formally define these integrals here. And similarly, if I look at this one here, the interval here is finite, right? But let's look at this function we're integrating. Is it continuous? Does it have an infinite discontinuity? What happens at x equals 1? Well, the denominator goes to 0 and the numerator does not go to 0, meaning we have a vertical asymptote at x equals 1. So we are integrating over a region that contains a vertical asymptote. So this is an infinite valued function. So this is a type 2 integral here. So type 1 means we're integrating a continuous or a function that does not have an infinite discontinuity over an infinite interval. In this particular example here, we are integrating something over a finite interval, but it has an infinite discontinuity. So what is an improper integral? An integral having either an infinitely discontinuous integrand, right, or an infinite interval. If one of these conditions are satisfied, then we say it's an infinite interval. Sorry, it's an improper integral. And the main catch here is the following. If you go back and hopefully you did this for your reading question here, you went back and you looked at the fundamental theorem of calculus, part 1 and part 2. And again, if there's one thing that's going to be on the final exam, it is the statement of fundamental theorem of calculus. is these are the cases where the fundamental theorem of calculus does not hold. All right, so the fundamental theorem of calculus does not hold for these types of integrals here. So there's type 1 integrals, there's type 2 integrals. They are either integral having infinite discontinuity in the region of integration, or we're integrating over an infinite interval. And in either cases, the fundamental theorem of calculus does not apply, which means we cannot do integration the way we've been doing it so far. So how do we evaluate these types of integrals is really what we're going to be talking about today. All right, so that's really the goal here today, is to figure out how to evaluate improper integrals. All right, so before we actually talk about formally, what I'd like to do is I would like to look at example 1 here, and we're going to move up and fill out the definition for type 1 improper integral, is we're going to see if we can make sense of this integral here. So what we're going to do is we're going to start off with the picture of 1 over x squared, and that was one of your reading assignment a few days ago. Right, so the graph of 1 over x squared, we don't care about what's happening on the left-hand side. On the right-hand side, it looks like that. So that's our 1 here. So what is this interval asking us? What is this integral really asking us? It's asking us, what is the area under the curve of 1 over x squared for all x bigger than or equal to 1? All right, so that's what this question is asking here. What happens to this area here as x gets larger and larger? So if it keeps going, this goes on forever, so we want to find the area as x goes on forever. All right, so how do we make sense of an area that goes on forever and ever? All right, so how do we make sense of it? So I might say, hey, let's compute this area, but since this keeps going on forever and ever, we have to keep going on forever and ever. The idea is going to be, what we're going to do is we're going to turn this question into a limit question here. So we're going to stop at this point here, which I'm going to call t. All right, and what I'm going to do is I'm going to find the area between 1 and t of 1 over x squared dx. All right, and I'm going to make this t larger and larger here, and let's see what happens to this area. In other words, I'm going to now then let limit as t approaches infinity. But now, look at this one here. Well, t is some number here, so the interval we're integrating over is a finite interval, and the function does not have an infinite discontinuity. Meaning, now we have a proper integral. Right? So all formal and proper. Meaning, if we have a proper integral, we can actually apply the fundamental theorem of calculus. Right? So, meaning now, I have this limit here floating around, but I can compute this integral here. So 1 over x squared, I can write as x to the negative 2. And the integral of x to the negative 2 is x to the negative 1 over negative 1. And as x goes from 1 to t. All right, so this now here becomes limit as t approaches infinity. Plug in t, so I get negative 1 over t, right? Because x to the negative 1 is 1 over x, minus negative 1. So it's that. So if I put these together, I get a limit as t approaches infinity, 1 minus 1 over t. And if t approaches 1 minus 1 over t is 1. So the area under 1 over x squared as x goes from 1 to infinity is 1. So so what's happening is as t gets larger and larger, the area under the curve is equal 1. So this is quite surprising, right? We are looking at a curve of infinite length. This curve keeps going forever and ever. But surprisingly, the area that is bounded by this curve and the x-axis is a finite area. Actually, it's not only finite, it's just 1. All right, and this is going to be the idea that we are going to use to evaluate improper integrals of type 1. All right, so type 1 improper integral means we are looking at an improper integral of a function of this form here. So f is going to be continuous. So we're looking at a continuous integral on our interval a through infinity. So for all value of x bigger than or equal to a, our function is continuous. In that case here, if we're integrating this continuous function over an infinite interval, we're going to call it a type 1 improper integral. And to compute this, we are going to turn it into a limit. And limit as t approaches infinity, a to t of f of x d of x. All right, so that's that. And now what happens if limit, if we are going from negative infinity to a? In that case, we're going to turn it into limit as t approaches negative infinity of t to a f of x d of x. All right, and in this case, we require that our function be continuous on negative infinity to a. All right, so if we have a type 1 improper integral, which means we are integrating a continuous function on an infinite interval, we're going to turn it into a limit, and we are going to now, once we have a limit, we can compute the integral, because since it's continuous and finite valued, we can use fundamental theorem of calculus, and whatever integral we get, we're going to take the relevant limit. And here's a few things here. So improper integrals are called convergent if the limit exists. All right, so we could compute a limit and the limit could exist or not, but not only does the limit need to exist and is finite, which means if we get positive or negative infinity, that is not convergent. And in that case, we say it is divergent if the limit does not exist or is infinite. All right, so that's what it means for it to be convergent and divergent. Convergent means finite value. Finite value means you should be getting a number out of it, right? So it could be 1 billion, or it could be 1 billion to the power 1 billion, but it's still a number. So that's finite. Infinite means that the limit is positive or negative infinity, and does not exist means the limit does not exist. Here's a remark. Now, if both, let's say of some number a to infinity, f of x, d of x, and negative infinity a to f of x, d of x are convergent, for some a, doesn't matter what a it is. So if we can find a number a such that from a to infinity and negative infinity to a our integral is convergent, then so is the integral from negative infinity to infinity f of x d of x. In other words, if we want to show integral from negative infinity to infinity of f of x d of x is convergent, we need to split it up into two integrals, from negative infinity to some number a, and then from that same number a to infinity. And if both of them are convergent, then so is that integral. And furthermore, in this case here, well, this is convergent means that's a finite number, right? It is a numerical value. This is convergent means we're going to get a numerical value. In that case, the integral from negative infinity to infinity f of x d of x is going to be the integral from negative infinity to a f of x d of x plus the integral from a to infinity of f of x d of x. So if both of these are convergent, we're going to get a number. And in that case, the integral from negative infinity to infinity is going to be the sum of those two numbers there. All right, so this is one of my favorite problems. All right, so what we want to do is we want to determine if this improper integral right here is convergent or divergent. Right, so whenever we see this, the first thing is going to be trying to figure out whether it's improper integral of type 1 and type 2. All right, so we have only talked about improper integrals of type 1. All right, so we're going to get to improper of type 2. Type 1 means we have a continuous function over this interval, but the interval is infinite. And the interval is infinite is clear. As for whether it is continuous or not, we can write this as x over e to the x. Both of these functions are continuous. So the only way this function would be discontinuous is if the denominator was equal to 0. However, since exponential is never equal to 0, this thing is continuous here. So on 0 to infinity, this function here is going to be continuous. All right, so we have an improper integral of type 1. The first thing we're going to do is we are going to turn it into a limit, right? So x e to the negative x is going to be limit as t approaches infinity, integral from 0 to t, x e to the negative x, where t is some number. Now we have managed to take this integral that was improper, turn it into a limit question, which we're going to leave for the time being, and a proper integral, right? Because this was continuous already. Now that we have gotten rid of the infinite discontinuity part, this is infinite interval part, this is now a finite interval, which means we can go about integrating this the way we want to integrate. So now, let's go back to integrals, right? We have a product of a polynomial and an exponential. We try substitution first, it doesn't work. No formula, no algebra, which means it's integration by parts. And remember LPET, logarithms, polynomials, exponential, and trigonometric, which comes before, x or e to the negative x? Well, the first is x, since it's a polynomial, so I have u is equal to x, dv is equal to e to the negative x, which means du is just dx, and the integral of e to the negative x, this is e to the negative 1 times x, which means I get e to the negative x divided by negative 1, which is negative e to the negative x. So if I put this together here, I have limit as t approaches infinity, which stays as it is, and then we have uv, which is negative x e to the negative x minus v du, which is negative e to the negative x, and all of this from 0 to t. All right, and now limit as t approaches infinity, I have negative x e to the negative x. That negative becomes positive, but then we need to integrate e to the negative x again. And the integral of e to the negative x is negative e to the x, so that gives us another minus here. And that goes from 0 to t. All right, so now let's plug in plug in t. So we have, when I plug in t, I get negative t e to the negative t minus e to the negative t minus 0 e to the negative 0 minus e to the negative 0. All right, 0 times e to the negative 0 is 0, and that here is 1. So I have limit as t approaches infinity, negative t e to the negative t minus e to the negative t minus negative 1, which becomes positive 1. All right, so what we've done here first is we realize it's an improper integral because of type 1. Improper integral of type 1 because it's continuous over that infinite interval, and we have an infinite interval. right? And we turned it into a limit, and then we realized we had to do integration by parts. So that's what we did here. All we've done is this is just integration by parts. Now what we would like to do is we would like to find the limit as t approaches infinity of e to the negative t of this quantity here. So let's look at e to the t first here. So remember, graph of e to the t looks something like that. So that's 1 here, and it keeps increasing, and here it keeps getting closer and closer to 0 without never ever reaching it. So what is the limit as t approaches infinity of e to the negative t? All right, so as t goes to infinity, negative t goes to negative infinity. And what is happening to exponential as t goes to negative infinity? It's going closer and closer to 0. So from this graph here, what I'm saying is limit as t approaches infinity, e to the negative t is equal to 0. Right? Because as t goes to infinity, as t gets larger and larger, negative t is getting smaller and smaller. And as this power is getting smaller and smaller, what's happening to the exponential is getting closer and closer to 0. So if I look at this quantity here, I have the limit of the first one is, as t goes to infinity, it's negative infinity times e to the negative t, which is 0. And I have negative infinity to the 0. What kind of limits do I have there? I have an indeterminate limit, right? This limit here, as we just discussed, is 0, and this is a constant, so that limit is 1. So what I have right now is I have limit as t approaches infinity, negative t e to the negative t plus 1. And this here is an indeterminate limit of the form infinity times 0. Remember, the goal whenever we have infinity times 0 is to turn it into a fraction, which is either 0 over 0 or infinity over infinity. All right, and in this case, since we have infinity times 0, I can flip it over. But what I notice here is this is e to the negative t, right? There's an easy way of turning that into a fraction. It is writing it as negative t over e to the t plus 1. And now, right, so just to indicate that plus 1's already taken the limit of, not that it matters. And now in this case here, I'm going to do L'Hopital's rule. So when I do that, I get limit as t approaches infinity. The derivative of t is negative 1 over e to the t plus 1. And now as t goes to infinity, e to the t goes to infinity, so this entire thing goes to 0. So I'm left with 0 plus 1, which is 1. All right, so what we have done is we've shown that this improper integral is equal to 1. Is that convergent or divergent then? Exactly, since we got that it's a finite number, it's convergent. And not only is it convergent, its value is equal to 1. Right, so that's how we deal with improper integrals of type 1, is we turn it into a limit so that the fundamental theorem of calculus does apply. So we've taken this problem of fundamental theorem of calculus not applying to a limit problem, and that's how we're going to solve it.